All right, the biggest thing is stability, okay? I think I taught this to DVF last year. Maybe I didn't. I don't know. On a conventional aircraft, you got let's say I have a rectangular wing here, okay? This wing is really a million airfoils sandwiched together. Right? If I took a knife and sliced the wing in half and then sliced it again like bread, and I looked at that, that wouldn't be an airfoil. It would have a finite thickness, but if I kept slicing it over and over and over again, got down to an infinitesimal level, I would have a two-dimensional airfoil, right? Let's assume, for this case, my wing is a flat plate. So I go back to my 2D airfoil analysis, and I go back to my flat plate theory, and I compute the pressure distribution across this flat plate, kind of like what I was showing Philip, and then I compute where lift acts. Lift is going to act at the aerodynamic center. For a flat plate, and only a flat plate, this is C over 4. If the math just comes out like that, all right? So it's 25% from the leading edge, okay? Now what that means is, if I have a rectangular wing, and I say, for this airfoil, my aerodynamic center is here, so this is like AC1. For this airfoil, my aerodynamic center is here, AC2, so on and so forth. And I do the other side. Where is my total aerodynamic center? This one's easy. Where is my total aerodynamic center of the entire wing? How far is it from the leading edge? 25, right? If they're all in the same spot, the total MAC, which is called the mean aerodynamic center, is going to be at 25% chord, because it's a rectangular wing, right? Now that's just of the main wing, right? What do you think is going to happen when you add a tail here? Say this is a flat plate. Where is the mean aerodynamic center of this guy going to be? Say 25%, it's going to be right here. So now you need to add up both of these together, am I right? But this wing is bigger than this one, right? So this is going to have a stronger effect. So the total mean aerodynamic center, I'm going to do a W here, is not going to be in the middle. It's going to be like here, because the main wing is huge. So I'm going to say that, let's say it's here. MAC is right there, okay? So that means the total lift of the entire aircraft acts right there, okay? So where do I put my CG?
Center of gravity?
Yeah, where do I put it? I'm a designer. I get to choose where to put it. Where do I want to put it? Here? Here? Here?
Yes.
In between the two.
Like right in the middle, right?
Yeah. There is a window called your static margin. If you put your CG too far forward, what's going to happen to the aircraft? It's going to nose down. How can you pull up? Could you pull up on the elevator and pull up? Yeah, but how big do you have to make your elevator to pull out of that? Okay, let's not do that. So I'm going to shift it this way. What happens if I get dangerously close and go to the other side? Now what's going to happen? Aircraft is going to be unstable and it's going to pitch up. So A, you want your static margin to be greater than 0 so that you're stable. And you also want it to be rapid. You also have some play with it though. If you make it really, really big, you have very stable aircraft. Your aircraft is going to be very sluggish, right? Because you have such a large moment arm to deal with, right? If you make it small, if you make your static margin small, your aircraft's going to be very twitchy and very maneuverable. But you need to be careful because if you go behind it, you're screwed, and your aircraft is going to flip backwards, which is exactly what happened to DVF last year. So what you need to do, and the reason why it happened, so why did it happen to DVF last year? This is very simple. You have a rectangular wing, they're both flat plates, everything's gravy, right? What if all of a sudden you make an aircraft that looks like this. Now what?
Very small center of gravity to choose from.
Your center of gravity can only be between here and here, and maybe not. I mean, maybe if you put a lot of weight in the back, you could move your CG back pretty far, you know? But if I look at every single airfoil, right? Here's AC1, here's AC5, AC16, you know, ACN. If I add all of those up together, where's my mirroring aerodynamic center going to be? Probably here, right? Who knows, right? And maybe it's not there. Maybe it's, say, here. Turns out we computed this for DBF, and it turns out I think it was like 13 inches from, no, it was 11 inches from the leading edge. Guess where the CG was? It was at 13. So now what happens to your aircraft when you try to take off? Flips backwards. And so if you talk to Min and you watch the video, it's exactly what happened. It flipped backwards 3 times. Not only that, they put a gyro on it, because it turns out the F-16, I think it's the F-16, actually has an unstable static margin. But what do they do to fix that? Because a pilot can't handle that. They put a very, very sophisticated stability augmentation system on it, SAS. And so the pilot doesn't have to worry about it. But you take an RC aircraft and just a human pilot and a simple gyro like the one that you find for $15, it's going to help it, but it's not going to entirely fix it. So even in the competition, the aircraft didn't flip, but it still flew straight up and then came crashing down. It was pretty bad. So this is something that you need to make sure. You need to compute all of your aerodynamic centers, add them all together, and compute the total aerodynamic center, and make sure that CG is in front. The second day of competition, what we did was we put a lead weight here, and we shifted the CG, I think, to like 9 inches, and then what happened? Aircraft didn't take off. So aerodynamic wings are really, really tough to dial in that stability or that static margin. And so that's why most aircraft and most trainers are this conventional design, because they're very easy. Because if you want to move your mean aerodynamic center, all you have to do is just move your tail back and forth. It's really simple to do. Okay. The next thing I had was structures and bending moment, but I think I kind of already touched on that. You know, if you make your wing larger and larger and larger, and SolidWorks has tools for those.
What about vibration?
Yeah, vibration in the wing is really a function of velocity, so and the moment of inertia of the wing. So if you have a very, very thin wing and you're flying fast, you're going to get a lot of vibration. You want to fly slower then. If you have a thick wing, right, if the area moment of inertia is thicker, then it's not going to vibrate very much. But it's strongly a function of velocity, because velocity dictates your dynamic pressure, which is, again, 1/2 rho v squared SCL. This is Q, your dynamic pressure. So if you fly faster, you're going to increase Q, and that is the energy added to the system. So if you add more and more energy, you're going to get a lot of vibration. I don't think they had any issues with that, because they made their whole thing out of carbon fiber and what was that? It wasn't balsa, but it was it's a step between balsa and carbon fiber. I forget what it's called. It was like a thin kind of plywood. Anyway, so they didn't have any issues with it. And again, the length of your wing is also going to dictate. All of those different parameters play a part. All right, well, I guess that concludes RC aerodynamic aircraft design in a nutshell.